with the Ingenuity Helicopter, a drone really, successfully touching down on the surface of Mars.
427 days. That's how long this mission has lasted, when it was only supposed to be 30 days. What began as a bold little experiment on Mars has turned into something much more, and now, maybe a tragedy. Nearly 300 million kilometers away from Earth, a tiny helicopter named Ingenuity, just 680 grams, lighter than a loaf of bread, sits on the surface of Mars. She's made from parts you could find in your garage. A smartphone processor, the kind of batteries you'd use in a power drill. Not exactly NASA's usual tech, right? And yet she worked. She flew, over and over, against every odd. But now something's wrong. Mars is changing. The planet tilts deeper into winter. At night, the temperature plunges minus 85 degrees Celsius. Winds grow stronger, the air turns mean, and thick dust storms begin to sweep the skies. The sun fades behind a brown haze. Solar power drains away. And on day 427, just like every day before, the team at NASA tries to reach her. They listen, they wait, nothing. They try again, silence. Back on Earth, at the Jet Propulsion Lab in Southern California, the mood is tense. The data says it all. Ingenuity might be gone. But the team refuses to give up. They have one last card to play, one final shot to reconnect with the first aircraft ever to fly on another world. Flashback 6 years. I visited JPL. That's when I first laid eyes on Ingenuity. She was small, strange, and surrounded by skepticism. Even some NASA scientists doubted her mission. Kenneth Farley, lead scientist for the Mars 2020 mission, said it himself. I was personally against it. Why? Because Ingenuity wasn't built to collect data or look for life. She was just a tech demo, a proof of concept, a gamble. NASA missions normally get billions in funding. Ingenuity got $80 million less than the budget for the movie The Martian. But this team, they believed. They had a vision. And on February 18, 2021, the Perseverance rover punched through the Martian atmosphere and landed safely. Clinging to its belly was Ginny, short for Ingenuity, quietly waiting for her moment. Sol Zero, her first day on Mars. Soon after, they detached her from the rover. She was on her own. The goal? Simple but wild. Prove that powered flight is possible in the thin Martian atmosphere. Mars has just 1% of Earth's air pressure. To fly there, Ginny had to be featherlight, and her blades had to spin at 2,400 RPM, a speed that sounds impossible for something so small. For 2 months, the team ran tests. Engine checks, navigation calibration, over and over. In that moment, history was made. Just 120 years after the Wright brothers took flight on Earth, humanity flew on another planet. And she didn't stop there. Ginny flew again and again and again. 5 flights in just a few weeks. What was supposed to be a 30-day mission had turned into over a year of success and discovery. But now, she's gone silent. The team is still listening, still hoping, because if Ginny taught us anything, it's this. Even the smallest, scrappiest machines can change history if you dare to fly. Mission accomplished. That was supposed to be it. Ingenuity was built as a tech demo, a quick 30-sol experiment. Fly a few times, prove it's possible, pack it up. We celebrate, maybe grab a beer, and move on. But something unexpected happened. It worked. It really worked. And when something works this well, NASA doesn't just let it sit still. Suddenly, there's a new developing. This tiny helicopter, barely bigger than a tissue box, gets asked to step up. Now she's not just flying for the sake of it. She's become the eyes of Perseverance, the Mars rover scouting ahead, exploring places too dangerous or remote for the rover to go. It's a huge win, but it's also a huge challenge. See, none of this was part of the plan. After Flight 5, every new flight was uncharted territory. We honestly didn't know, will we make it to Flight 7? Will we even survive to Flight 10? There were no protocols, no long-term strategy. We were in the deep end without floaties. Up until then, every single flight had been choreographed to perfection, tested hundreds of times in JPL's wind tunnels. simulated tens of thousands more, and every launch happened from carefully chosen, rover-scanned, satellite-approved terrain. But now, Ginny had to keep up with Perseverance, and that meant flying into places we didn't fully understand. And flying on Mars is nothing like flying on Earth. Mars is 56 million kilometers away at its closest. That means it takes about 6 minutes to send a signal and 6 more to get one back. Problem is, Ingenuity's flights last only 2 minutes. So, live piloting? Not an option. Instead, JPL programs the flight path in advance for Sequity Plinger. Once she takes off, she's completely on her own. But even before she can fly, NASA has to know where she is. No big deal, right? Just use GPS? Well, not so fast. Here on Earth, GPS depends on a network of 24 satellites. Mars has only 7. GPS simply doesn't work there. So, Ginny uses a much simpler trick. Cameras. She's got 2. One looks forward, a 13-megapixel color camera.
It's clever, and it usually works.
But not always. Flight 6 was her first trip outside the safe zone. 54 seconds in things go sideways, literally. Suddenly, she starts wobbling violently, tilting 20 degrees back and forth. Emergency flags trigger. The team watches in disbelief. What went wrong? Turns out, it was a camera glitch. See, the color camera added late in the build wasn't fully tested with the system. And during this flight, one of its images arrived at exactly the same moment as a black and white image. The software got confused and dropped the black and white photo. That one dropped frame created a domino effect. Now, every new image was 1 frame behind. The navigation system thought Ginny was falling behind, even though she was right where she should be. So it pushed her forward. She sped up, overshot, tried to correct, wobbled, overcorrected again. It created a feedback loop like a car swerving on ice, each adjustment making the skid worse. It was a mess, but she made it. She landed. Shaken? Yes. Broken? No. Even when the system failed, Ingenuity finds a way. She wasn't built for this, but she's flying anyway, and somehow that's the story of her entire mission. It was just 1 frame. That's all it took to throw everything off 1 single camera image out of sync. Any more than that, and Ginny might have spun out of control. Crashed. Mission over. But she didn't. She caught the error in real time and made an emergency landing before things spiraled out of control. Barely. Once safely back on the ground, the JPL team dug into the problem and found the bug. They patched the software fast. Crisis averted. And somehow again, Ginny pulled through. Over the next dozen flights, she kept pace with Perseverance, scouting ahead, collecting data, helping guide the rover's search for signs of ancient life. Then came Flight 19. The team was ready, everything was prepped. But the day before launch, a phone call came in. There's a dust storm building over Jezero crater. Flight cancelled. Plans scrapped. Time to hunker down and wait it out. The storm hits hard 6 days of punishing winds, gusting up to 20 meters per second. It was the first major Martian storm of that season, and it hammered them. But Ginny, she made it. No crash, no topple, just sitting there, alive and intact. Unfortunately, she didn't escape unharmed. Now there's dust, and on Mars, dust is more than just dirt in the wind. For Ingenuity, it creates 2 big issues. First, her solar panels are coated, cutting down her energy by 18%. That's a huge hit for a helicopter running purely on solar power.
NASA knew dust could be a problem,
But Ginny was a tech demo. There wasn't time or budget to build in perfect fixes, so they improvised. They shortened flights to deal with reduced power. And for the jammed parts, they just kept wiggling the servos gently again and again until the dust shook loose. Eventually, it worked. She flew again. Not perfectly, but she flew. She was battered but still in the air, and now the fight to survive only gets tougher. Mars might look calm in photos, but it's brutal beneath the surface. Every Martian night, the temperature plummets. There's barely any atmosphere to trap heat, so whatever warmed builds during the day just disappears into space. My friend Alex from the channel Astrum put it like this: if you were standing on the equator at midday, your feet might feel a comfy 73 degrees Fahrenheit, 23 degrees Celsius, but at head level, it's freezing. Literally 32 degrees Fahrenheit, 0 degrees Celsius. And at night, temperatures plunge to minus 133 degrees Celsius. That's about minus 207 degrees Fahrenheit. That's not just cold, that's death for machines cold. And it's only getting worse. Mars is moving farther from the sun, slipping deeper into its long, harsh winter. Each night, the temperatures drop lower, the sunlight gets weaker, the dust hangs in the air longer, and Ginny, she's still out there low on power, joints grinding, freezing every night, and somehow still rising into the sky. Here's the thing about Ingenuity. She's tough, but she wasn't built to last forever. A lot of her key electronics, hand-soldered. Not fancy space-grade tech, just smart, scrappy engineering. And when you're dealing with wild temperature swings, like the ones on Mars, warm by day, absolutely freezing by night, those soldered joints expand and contract. Over time, that tiny movement can break the connections completely. Now, inside her batteries, there's a special liquid called an electrolyte. It's what lets lithium ions flow during charging and discharging. But if that liquid ever freezes, it's game over. No power, no heat, no flight. Just a frozen drone stuck on a frozen planet. So NASA had a solution. They built something called the Warm Electronics Box. It's basically a tiny heated shelter inside Ginny, and it keeps her most vulnerable parts from freezing overnight. The heaters run at night, and the energy to run them, that comes from her batteries. And that trade-off is brutal. Ginny might use 25 to 30% of her power to actually fly. The rest? Just staying warm, while Mars tries to freeze her solid. But the colder it gets, the harder those heaters have to work. And if they can't keep up, the batteries get cold too. And cold batteries? They don't work as well.
May 3rd.
The team at JPL shows up for what they think will be another ordinary day. They check the latest data downlink from Mars. Nothing. They ping her. Still nothing. Did they just lose her? Is this the end of the line for Ingenuity? They don't panic. Not yet. Instead, they go into troubleshooting mode. Let's check every angle, rule out every possibility. They keep digging until they land on one theory that makes sense. Here's how Ginny was designed. She's got a digital alarm clock built in. It wakes her up. She listens for a signal from Earth for 15 minutes. If she hears nothing, she goes back to sleep until the next scheduled alarm. Now, what if just maybe Ginny got so cold one night that she fully powered down? Batteries empty, heaters off, everything frozen. But if that happened, and she survived, then when the sun comes up and her solar panels start charging again, she might reboot. Problem is, when that happens, her internal clock resets, so her wake-up schedule would be off by a lot. The JPL team recalculates. If she's alive and recharging, she should now be waking up around 11:45 a.m. Martian time, not the time they'd been trying to contact her. So, they shift the timing and start sending out pings again. Ping, ping, ping. Then finally, she answers. She's alive. After all that, after freezing through a Martian night, Ginny's systems boot back up. Every component inside her warm box was only rated down to minus 45 degrees Celsius, but somehow they all survived. Except one. The inclinometer. Dead. That's the part that tells Ginny which way is up before she takes off. Without it, she can't get her orientation. Imagine trying to fly while tilted 10 degrees in the wrong direction on Mars. You could fly straight into a cliff. The team's first reaction? Panic. No inclinometer, no flight. But then someone remembers. Wait a second. Ginny's built from phone parts, literally. Her processor is from a Samsung Galaxy S5. Her sensors? From a Google Pixel 3. And what do all smartphones have? Accelerometers, tiny chips that can track motion, orientation, and acceleration in 3 dimensions: X, Y, Z, using little masses suspended on spring-like arms. It's basically physics at work. As that mass moves because of acceleration or tilt, it changes the charge between tiny plates, like a capacitor. Those changes can be measured and used to figure out how fast something is moving and in which direction. So the engineers think, why not use those? Why not reprogram Ginny to use her phone-grade accelerometers as a backup for her dead inclinometer? It's a long shot, but it just might work. Ever wonder how your phone knows when to flip the screen?
And here's the crazy part.
Ingenuity, NASA's Mars helicopter, uses the exact same IMU as the Google Pixel 3. Yep, the same kind that's been in millions of smartphones. So, when the inclinometer on Ginny failed the thing that tells her which way she's tilted before flight, the engineers at JPL had a bold idea. What if we just reprogram her to use the IMU instead? See, an inclinometer is really just a fancy way of reading accelerometer data to figure out your roll and pitch, your basic orientation. And since the IMU has accelerometers too, they figured, why not just use that instead? And it worked. They pulled Ginny back from the brink. In fact, they got lucky. Of all the parts that could have failed, the only one they could afford to lose was the one that broke. But the story doesn't stop there. See, those parts have processor, sensors, even the IMU. They're not space-grade. They weren't designed to survive the harsh environment of another planet. They're just off-the-shelf components, like the ones in your phone. And on Mars, the atmosphere is so thin that cosmic rays, the high-energy particles zipping through space, can actually hit the surface. A single cosmic ray can strike a computer chip and flip a bit in the memory. One little change, and suddenly your software thinks 0 is 1, or vice versa. Here on Earth, this already happens. In one Belgian election, a cosmic ray once added 4,096 phantom votes to a candidate out of nowhere. Now imagine something like that happening mid-flight on Mars. One flipped bit equals total mission failure. So why doesn't Ginny crash? 10 years ago, if you told NASA you wanted to fly a smartphone processor in space, they'd laugh you out of the room. It'll last 2 days before a cosmic ray fries it, they'd say, but here's what actually happened. The parts held up, surprisingly well. Cosmic rays? Not as big of a threat as everyone feared, and that's a huge discovery. Instead of spending years and millions of dollars designing space-hardened chips from scratch, engineers can now just buy commercial processors in bulk, run radiation tests on them, and pick out the winners. Some chips perform poorly, sure, but others, they just work. No one's quite sure why, but they survive, and that's all that matters. Thanks to this smart, cost-effective approach, Ingenuity made it through the brutal Martian winter, but just barely. She managed to stay close enough to the Perseverance rover to keep talking to it. And even though her parts were never supposed to last this long, she's still flying. Spring arrives on Mars. Okay, no birds chirping, but the spirit? Totally there. Over the next 41 flights, Ginny crushes it. She soars over craters that the Perseverance rover could never reach. She snaps stunning images of the Martian landscape from high above views that no spacecraft has ever seen. She starts pushing boundaries, testing the limits of flight on another planet. But here's the thing, the faster she flies, the tougher navigation becomes. See, Ginny relies on visual cues, features on the ground that her cameras track. Fly too fast and those features zip by so quickly that the system can't lock onto them. So how do you fix that? Fly higher. By gaining altitude, the ground features appear to move slower in the frame, giving her cameras more time to react. JPL bumps her altitude from 10 meters all the way up to 24. The result? Speed jumps from a casual 2 meters per second to a blazing 10 meters per second. Records are shattered. Fastest flight, highest flight, longest distance. They're rewriting the book on extraterrestrial aviation, just one flight at a time. They know this moment, this chance to fly a helicopter on Mars may never come again. So they push every limit they can. And it works. Ginny and Perseverance make it all the way to Neretva Vallis, a dried-up river delta at the edge of Jezero Crater. They're a dream team, a rover and a helicopter exploring an alien world together. Then, Flight 71 happens. And this time, the problem is bigger than anything they've faced before. Now, Ginny doesn't carry much. Her only scientific instrument is a camera. But that one camera takes hundreds of photos every single day, transmitting them back to Earth. Perseverance does the same, including one awesome selfie with Ginny. Honestly, they're probably the most online duo in the entire solar system. They share everything. Photos, coordinates, system updates. We always know where they are and what they're doing. And if you think about it, isn't that us too? We're constantly sharing data, whether it's location, habits, preferences. But unlike Ginny and Perseverance, our data doesn't just land in some secure NASA archive. It gets bought, sold, and used, often without us even knowing. There's just one final stretch in this chapter. She needs to cross a sand dune and make it to a location called Bright Angel, where she'll link back up with Perseverance. Easy? Not exactly. But after 70 flights, dust storms, freezing nights, hardware failures, and speed records, Ginny isn't just surviving anymore. She's making history. Flight 71 was supposed to be routine. Ginny lifted off. Everything seemed fine until about 10 seconds in. Her navigation system started acting up. Something was off. Before anyone could intervene, she triggered her emergency landing mode and came down hard. The team at JPL holds their breath. They ping her, and to their relief, Ginny had flown over a stretch of smooth, sandy terrain. No rocks, no distinctive features for her camera to lock onto. Without visual landmarks, she couldn't figure out where she was. It's déjà vu from Flight 6, but this time there's no quick software fix. This is just a limitation of the terrain. So, they check her over for damage, rotors, structure, instruments. Miraculously, everything still seems intact. Time for a cautious next step. They plan the simplest possible flight, straight up, take a few photos and straight back down. Ginny lifts off for Flight 72. She climbs, takes her snapshots, and on descent, the same navigation issue strikes again. But this time, it's not survivable. Perseverance, her rover companion, rolls up and captures a heartbreaking image. Ginny, downed. Her rotor blades shattered. Seeing that first photo from the crash site, that hit hard. The team had held out hope. Maybe another rough landing, but she'd bounce back like last time. But this looked final. So what changed? Flight 71 was also a rough landing, same navigation problem. But she made it through that one, why not this time? And now, they're doing something no one's ever done before. The first aircraft crash investigation on another planet. That's right, first helicopter on Mars. First air crash on Mars. They study the wreckage. Pieces of the blades are scattered across the site. But something's strange. Where's the impact pattern? Normally, if high-speed blades hit the ground, you'd expect a distinct strike mark, a gouge, a spray of debris, a violent scatter, maybe even visible from orbit. But here, nothing. No clear blade strike zone. No signs she slammed into the surface mid-spin. So what really happened? They start piecing it together. Someone pulls out a prototype rotor blade from Ingenuity's early development days. It's nearly identical to the ones she flew with. And now, the team starts digging for answers, frame by frame, clue by clue. Because this isn't just the story of a machine that fell. It's the story of how far we pushed a flying robot on another world and how we learned from the end as much as from the beginning. So the rotor blades on Ingenuity, they're made from a carbon fiber composite with a foam core. Super high-tech but feather-light. Seriously, when you pick one up, it almost doesn't feel real. Whoa! This thing's way lighter than it looks. You expect weight, but it's like holding a prop from a sci-fi set. It doesn't even feel physical. But that leads to the big question. Why did they break? Let's break it down. When Ginny's blades spin, the tips trace out a giant circle in the air. Imagine a hula hoop spinning flat above her. Now, you'd think that the blades are spinning fast. So, when you apply force, say from an impact or strong wind, the actual movement of the blade doesn't happen right at the point of contact. Instead, the biggest flex or bend happens 90 degrees later in the rotation. This weird delay? It's a phenomenon called gyroscopic precession. Same thing happens when you twist a spinning bike wheel and it turns in a direction you didn't expect. It's counterintuitive but totally predictable. Now, here's where it gets even more interesting. Ingenuity doesn't have just one rotor, she has two, spinning in opposite directions. That's important, because each set of blades experiences that precession torque, but in opposite directions. So overall, the twisting forces cancel out for the helicopter. But individually, each blade still flexes and twists under stress. And there's a key weak point, the exact spot where the reinforcement inside the blade tapers off. So, if something goes wrong, like a sudden jolt or impact, you'd expect the blade to snap right there. And guess what? That's exactly what we see in the wreckage from Flight 72. There's this jagged edge where the blade tip sheared right off. You can literally see the spot where it failed. So what happened? On Flight 72, Ginny came down hard. She didn't just land, she slammed into a dune, and at an awkward angle. That impact force didn't just bounce off the landing gear, it shot up through the helicopter's frame. And when that force hit the spinning rotors, it triggered a huge precession torque. That torque bent the blades mid-spin until they just couldn't take it anymore. Snap, right at the stress point, just like the physics predicted. And yet, get this, everything else held up. The landing gear, still intact. Avionics, working. Servos, not fried. She took a serious hit, but it was only the blades, the most delicate part, that broke. It's kind of amazing. The very thing that made Ingenuity fly also ended her mission, but not before she rewrote the rules of flight on another planet. So, the swash plates, all good, totally intact, but the rotors, that's where the weak link was. And now, the engineers know exactly what needs to change. Enter the next generation, Chopper, the future of Martian flight. Remember holding an Ingenuity blade? Well, here's the next-gen baby blade. Looks pretty similar at first glance, but there are a few key upgrades.
First off, these new blades are reinforced,
Designed to handle the torque from those brutal, uneven landings. No more snapping under pressure. And here's the big one. Chopper doesn't just have two rotors, it's packing 6. That means more lift, more stability, and more payload. This thing can actually carry its own scientific instruments now. Yeah, you heard that right. Chopper isn't just tagging along anymore, it's doing science on its own. Even cooler, they've developed a lightweight radio that can beam data straight to orbit. No more needing to stay close to Perseverance for comms. We're free now. We can explore anywhere. And that's huge, because Ingenuity always had to stick close to the rover. But Chopper's its own spacecraft. That little blue box on board, you can load it with up to 5 kilograms of science gear, and then fly it literally anywhere on Mars. 3 kilometers per sol, just like that. Zip across craters, scan ridges, land somewhere new, in minutes. No wonder the science community's buzzing. This changes the game. Now, the version you're looking at is a 5th scale model, but it's already showing what's possible. See, the full system is made up of 2 parts. The top, that's Chopper, the exploration platform that'll one day cover the whole Martian surface. But underneath, that's where things get clever, a mid-air deployment system. Basically a flying launch pad. Because here's the deal, landing a rover on Mars, complicated. You need a whole sky crane. But with Chopper, all you need is a platform. Drop through the atmosphere, land the rig, and then the helicopter just flies off. Simple, clean, revolutionary. We've got this rocket-powered jetpack we use to slow things down just enough to hit that sweet spot where flight is actually controllable. That way, we can take off mid-air and land on our own power. But to pull that off, yeah, we need rockets. 3, 2, 1, liftoff. It's wild, but this isn't just a one-off mission. This is the beginning of something big. We're talking aviation, becoming the future of exploration on Mars. In fact, in my head, there's no doubt about it, it's going to happen. One day, fleets of aircraft will fly across the red planet. There'll be airports on Mars. We'll see rotorcraft the size of Chopper, others the size of Ingenuity, and even larger ones soaring above ancient canyons and dusty plains. All because of Ginny. NASA once questioned whether this was even possible. Ingenuity was a long shot, a high-risk side project. But she changed everything. Think back to the late 1800s. If someone told you, "Hey, I'm going to build a machine that lets people fly," you'd probably laugh and say, "All right, buddy, have fun breaking your neck in the garage." But then came the Wright brothers, and suddenly, flight wasn't a fantasy, it was real.
That's exactly what happened here.
Ingenuity is Mars's version of Kitty Hawk. And that's why, strapped beneath Ginny's belly, there's a tiny 1 centimeter square of muslin fabric, cut from the original Wright flyer, from the first flight on Earth to the first flight on another planet. Now, Ginny may not be flying anymore, but she's not done. She's still out there, right now, on the Martian surface. Not just lying still, she's working, taking photos, recording temperature readings, monitoring weather patterns every single day. No one ever expected that, especially after Flight 72. If you'd asked the team, what happens if she crashes, they'd never have guessed. Well, maybe we still get a fully functioning weather station. But that's Ginny. She's built like a tank, and the team, they couldn't be prouder. Not just because she flew, but because she proved what's possible. And she paved the way for the next generation to fly even farther.